SwayamPrabha. Digital India. Educated India.
Having done free oscillator and shown you the phenomena of resonance, now let me go to forced but damped oscillator. In this case, the equation of motion of which you are by now experts is going to look like mx double dot plus bx dot plus kx is equal to f cosine of omega t. Dividing by m, I get x double dot plus b over m I have been writing as gamma x dot plus omega 0 square x equals f over m cosine of omega t. Again, as in the case of free oscillator, I would have the general solution as the sum of the homogeneous part solution and a particular solution. So, I am going to have x t as equal to x homogeneous plus x particular, where the particular solution belongs to what force I am applying and the homogeneous solution has those two independent constants. In general, this therefore would be e raised to minus gamma over 2 t. This we have solved in the previous lecture. C cosine of omega 1 t, where omega 1 is slightly different from omega 0, plus d sine of omega 1 t. This is the homogeneous solution plus x particular t. So, let me rewrite the solution for a forced damped oscillator. We have x t is equal to e raised to minus gamma over 2 t c cosine omega 0 t plus d sine of omega 0 t plus x particular. As t becomes large, you see that this term would go to 0, and therefore, in the limit of large t, I am going to have only x particular solution. This does not get damped out, and this is known as steady state. Solution, because by now its own part has died down, and the only solution is because the oscillator is being driven and it achieves a steady state where because of the force it keeps on moving in a very steady manner, and therefore, this is known as steady state solution. For the time being, we will focus on this solution. So, the equation that we are solving is x double dot plus gamma x dot plus omega 0 square x is equal to f over m cosine of omega t, and I am looking for its particular solution because in the limit of large time that is the only solution. So, in other words, I am looking for steady state solution. I could try a solution like x equals some amplitude times cosine of omega t. However, you see that when I take its first derivative to put in this term, I get a sine omega t term. Therefore, in general, I should look for a solution of this form, a cosine omega t plus sine omega t. So, you see right away that the solution is not in phase with the applied force, or its phase differs. Let us see now what the general solution is. So, let us put this in here. X dot then would give me minus omega a sine of omega t plus omega b cosine of omega t. When I substitute, an x double dot is equal to minus omega square a cosine omega t minus omega square b sine of omega t. When I substitute these three, in this equation, I am going to get and collect cosine omega t and sin omega t terms together, I am going to get cosine omega t minus omega square a. From this term, I am going to get plus gamma omega b, and from the last term I am going to get plus a omega 0 square plus collect the sin omega t terms, and I am going to get minus omega square b minus omega gamma omega a plus omega 0 square b is equal to f over m cosine of omega t. Since on the right hand side there is no term of sin omega t, therefore, this term must be 0, and this term minus omega square a plus gamma omega b plus a omega naught square must equal f over m. So, we have minus omega square b minus gamma omega a plus omega naught square b is equal to 0, and we have minus omega square a plus gamma omega b plus omega naught square a is equal to f over m. When you solve these two equations, and I leave it for you as an exercise, you are going to get a is equal to omega naught square minus omega square over omega naught square minus omega square plus gamma square omega square, and b is equal to gamma omega over omega naught square minus omega square plus gamma square omega square. And therefore, the solution, steady state solution, is going to be omega naught square minus omega square or times f over m also times f over m. F over m over omega naught square minus omega square plus gamma square omega square cosine of omega t plus gamma omega f over m over omega naught square minus omega square plus gamma square omega square sine of omega t. Look at these two terms. I will take square root of the denominator out and write the solution as x t is equal to f over m over square root of omega naught square minus omega square plus gamma square omega square times omega naught square minus omega square over square root of this term cosine omega t. Let me write this once, omega naught square minus omega square plus gamma square omega square plus gamma omega over square root of omega naught square minus omega square plus gamma square omega square sine of omega t, and this can be written as some amplitude times cosine of omega t minus phi, where the amplitude of the motion is f over m divided by square root of omega naught square minus omega square plus gamma square omega square, and sin phi is gamma omega over square root of omega naught square minus omega square plus gamma square omega square, or the square here. Cosine phi is omega naught square minus omega square over square root of this whole quantity, and tangent phi is gamma omega divided by omega naught square minus omega square. So, when I solve for x double dot plus gamma x dot plus omega 0 square x equals f over m cosine of omega t, I get a solution x t, which is equal to amplitude times cosine of omega t minus phi, where amplitude is f divided by m over square root of omega 0 square minus omega square square plus gamma square omega square, and tangent phi is equal to gamma omega over omega 0 square minus omega square. Notice that the displacement of the harmonic oscillator is now lagging behind the applied force. It is omega t minus phi. So, it responds slightly later. The amplitude depends on the frequency and obviously the force, how much force you are applying, and how much is lags behind depends only on the frequency and how much damping is there. More the damping, more the lagging behind, which is sensible from physical point of view. So, if I look at the phasor diagram at time t equal to 0, if this is the force, the displacement, obviously the magnitude is going to be slightly different, but if I just look at the phase relationship, is going to lag behind by this angle phi. If we translate this into the graph for displacement versus time, the applied force is of the form cosine omega t, f t is of the form f cosine of omega t, whereas x t is of the form some amplitude cosine of omega t minus phi. That is going to be slightly behind. So, it catches up with this displacement slightly later. So, this displacement is going to look something like this. This is x t, where this amplitude is f over m 1 over square root of omega naught square minus omega square plus gamma square omega square, and this phase angle is given by tangent phi equals gamma omega over omega naught square minus omega square. Notice that the steady state solution does not depend on the initial conditions. The initial conditions, whatever they did to the motion, have died out. Compare this with the situation that we solved earlier. For an undamped oscillator, the initial conditions affected the motion all the way, but here they die out because of the damping term, and the steady state solution depends only on the applied force. The solution has a nice geometric interpretation in terms of phasors. Let us see at time t equal to 0, I am applying a force which is in horizontal direction. The net displacement is behind this by an angle phi. This is net displacement in this direction. So, this gives you a force which is omega square a. The velocity is in this direction. So, this is term which is x double dot. The velocity is this direction, which is gamma omega a. This is proportional to x dot, and the spring's own force is in the direction. As far as getting the solution of damped harmonic oscillator, which is forced, is concerned, we are done now. We solve for x double dot plus gamma x dot plus omega naught square x equals f over m cosine omega t, and got a steady state solution. Let me write it as steady to emphasize state solution as a function of time. It looks like f over m divided by square root of omega naught square minus omega square plus gamma square omega square cosine of omega t minus phi. This is a complete solution. The motion, the displacement lags behind the applied force by a phase phi, and it has an amplitude that depends on the force and the applied frequency. What remains to be done now is to analyze different situations.